Hi, welcome to my talk on how to guarantee your machine learning model is going to fail on first contact with the real world. My name is Jesper Dramsch and I'm a machine learning engineer. I have experience building deep neural networks on satellite data, subsurface, geoscientific data. I really like to work on Kaggle notebooks and share more simpler models like random forests. And yeah, I've also successfully worked on some hackathon projects. So I really like machine learning, from supervised to unsupervised, shallow, deep, it's fascinating. But today, we're going to have a bit of a look at a different dimension of machine learning. While all of this is a bit tongue-in-cheek, it's very important to see that in real-world applications, there's nuance. So you'll have to see that sometimes you actually have to do some of this to make it work. First one, easiest one, 99% accuracy. Now, what does that actually mean? In this case, out of 1,000 samples, 2 are only wrong. And that usually means that you're not really dealing with real-world data. You're probably dealing with a very clean data set. Real-world data is messy. This is one of my favorite examples. Those are blueberry muffins and chihuahuas. And even humans have problems telling them apart. Be it label noise, like mislabeling something, or be it actually having really complicated data. 99% accuracy is rarely achievable on real-world applications. Some of the stuff that we have to do, which usually gets our metric a little bit lower, is data augmentation. So this cute animal, if you only train it on the original data, then your machine learning model for wildlife cameras or whatever you're doing is going to have a problem if it's getting up and close, really inspecting the camera. Your neural network will not understand that unless you train it to. Usually that means that your metric evaluation is getting a bit lower. That's why on Kaggle, for example, we often train all the epochs with augmentation. And then as a trick, the last epoch is going to be trained on the original data to kind of get the variability in the data, but then kind of fine tune your network on the, on that peak of the probability distribution. To really have your model crash and burn, you have to absolutely ignore overfitting and data leakage. Overfitting, just to recap, is the idea that you have some kind of underlying model, the true data. So in this regression model right here, we have a polynomial of degree 4. It does a really good job of approximating this data. Now, a linear model is too simple to really capture the variability and the complexity of your data, but the 15 degree model is, it captures every data point in the training set. But if you give it new data, this new data will not fit on the prediction. So what that means in this trough right here, or in this peak right here, you actually have massive errors just because your model is much too complex and overfit on your data. Data leakage is something that not enough people know about, actually, and it's something that I learned on Kaggle. This satellite data was supposed to identify either ships or icebergs in the sea. And the problem was the icebergs were all taken from one acquisition, so the incidence angle was similar for all of them. So actually the winning solution ended up using mostly that feature to predict the right outcome and win a significant amount of money with a model that was absolutely useless on real world data. You may be thinking, okay, but what's the point? Well, in a hackathon, I had that problem with my own data. In the data cleaning process, we forgot to take out one column, and that column was actually directly predictive of our labels. So we had data leakage in our in our model, and it was performing really well. And we realized that, and we had to do the entire data processing again because we forgot to take that out. To be really careful, and it's usually a manual process. Like, the machine learning model isn't going to tell you, oh, this feature is essentially your output feature. Like, you have to really dig in and do your job as a data scientist. To make it really crash and burn, you have to assume everything is IID. What's IID? Basically, it means your data is independent and identically distributed. Every data point is generated independent of each other data point. And that the distribution of these data points is identical for all data that you get. Now, in the real world, unfortunately, my background is geoscience, so we'll have a quick look at rocks. In the real world, a lot of data depends on each other. So, for example, this beautiful mountain range right here exists because rocks were deposited on top of each other, and that deposition is usually dependent on the rock before, and the identical distribution is another problem. In these rocks, you can see some layers, some very interspersed layers, very thin layers are different than the other. You have that a lot, class imbalances. And the problem with a lot of machine learning is they assume IID, and that means the machine learning model will quickly learn, in this case, that predicting green will get it 70% there. So we have like 45,000 green, 25,000 non-green. And if you just take the accuracy of that, your machine learning model is shifting the standard case to be just the green. And that's usually not good. To make your model really, really bad, just use accuracy. It's good. It works. Well, it doesn't for imbalanced data a lot of times. So basically what you want to look at is the F1 score and definitely the ROC-AUC curve, so the area under curve, because those are exceptionally good at explaining how the decision is made, looking a little bit more into false positives and false negatives. What you do is you choose a loss function that is appropriate and basically models the true cost of your data. In neural networks, when we do semantic segmentation, so when we find objects in our images, self-driving cars are using exactly this segmentation to basically say, this is the lane, there's a bike over there, and that's all by doing the outlines and the classification of your images that are taken. So for this, you have a lot of different choices of metrics as well. The IOU is a classic where essentially you're aligning these maps with the maps where you know it's supposed to be. The cross entropy is always doing quite well, which is also used in classification. Knowing what you need them for is sometimes really important, but also just trying what works. This is a classic and it's a contentious topic. Collecting more data. We're living in a big data world these days. We're talking about petabytes at this point, exabytes, like these huge amounts of data. Data isn't equal to ground truth. But let's have a look at CERN. Those are the people that invented the internet and are the physics researchers of our times. What they do is they throw away most of their data. They do these collisions of protons and collect all this kind of data, but they know what data they're looking for. So this data is already heavily filtered when it goes on the hard disk, because if they, even with the data they're collecting, that's at 25 gigabytes per second, they have hundreds of petabytes of data already after filtering it. And the amounts of data they would have without filtering is it would just not be possible. Not physically, not technologically possible to collect. So thinking that data is ground truth is already faulty in physics. Geophysics data is interesting because You have so many things influencing it. And in the end, for every use case you have to reprocess the data. So do a different pre-processing before you do interpretation and whatever you do with geophysical data. Going more into the social side of things, taxonomies, how you classify things, are often decided by people beforehand. And like one of the more morbid taxonomies in ImageNet, something all of us are using, is the person class has a subclass called loser and failure, where there's a kid with shades in there, like sunglasses. That's not great. And if we go to the GPT-2 model, which is the last OpenAI model, GPT-3 is now the latest one that they have, but GPT-2 was trained on mostly Reddit data. So they went through Reddit and had a look at all different links. And the problem is there's a lot of conspiracy theories on Reddit. So if you actually ask it about geoscience, a lot of times you will get answers pertaining to a flat Earth, for example, and that's not great. Reusing these models that were trained from a data source that is unscientific, for example, like this is the case, can be really problematic. Just collecting more data, like getting more Reddit comments is easy. People are writing these every day, every second there's new comments. But it may not be the highest quality source of information that you can get. Strategies that sometimes work is if you have human interpretations. So for example, on medical data, you often ask radiologists to do X-ray interpretation. You want multiple people to interpret the same image, because even though it's kind of the same thing, the interpretation varies from person to person. And what's interesting also is that interpretations vary from yourself to yourself. So really good data sets go back to the same person 6 months later, a year later, and have them reinterpret the same data. So you have this inter and intra-interpreter variability in your data set captured. That's how you get good human interpreted data. Another thing that you can do is question and maybe change questionable taxonomies, like the loser one. Have a look into this and don't accept this as what it is. I think we all can do better and we all can make this world a little bit nicer, even though we're just a data scientist, just using this. And if you do want to collect more data to get better results, don't go to the same sources. So in my example of doing satellite image classification, right now we're collecting data, and basically what we decided to do is collect data in as many different positions in the country as possible. So we get a representative sample instead of just more data. Because if we have a lot of data from the same area, we get really good at that area, but basically we have no idea of what's really happening in all the other places. Cross-validation. We all do validation, right? We have to. It's the only way for us to know that our model is actually doing anything significant. Now, cross-validation is taking this a little step further, but it's absolutely necessary, like actually necessary, no joking here, to build good models. If you do not do cross-validation, your model is probably not performing well. And how that works is you split your training data in different folds and train on all except one, and do that all the way around. Like if you just do random sampling, you have the same problem as before with the imbalanced data. So what we do there is stratifying. So right here you see our smallest class is still split up in 4 parts in this case. The medium class, also 4 equal parts. So we really make sure that even in each fold right here, we have a representation of all distributions, which goes back to IID, right? We want this to be identically distributed. So all our classes have to be present in all of our folds for the cross-validation. It's very important. And stratification, really good to maybe make our model not crash and burn. We have the identical distribution. Now looking at independence. Time series, there's always a dependence in time. We have one data point, the next data point depends on the data point before. So in time series, we can do a time series split. So basically always predict the next step, the next time epoch. Going back to geographical data and geoscience data, this data is always somehow correlated in space. So if I have my satellite data, if I were to just pick random samples out of that, that would mean that I get a lot of samples in the training set that are right next to data in my validation set, which is kind of cheating because they're basically next to each other. Look back to the mountain range. If I get points that are even 10, 50 meters apart, that means I'm basically predicting on my training set. So what we do, instead of doing the random splits, is that we do blocks and we do cross-validation across blocks. A lot of times we have to do cross-validation on our pre-processing. There have been cases in biostatistics where published research was found to actually have null results when the pre-processing was included in the cross-validation. So basically the data was unintentionally probably handpicked in a way that there was then a signal in the data which actually wasn't there. Always include your pre-processing steps, your data selection steps in the cross-validation. Really important tips for doing cross-validation right, but cross-validation isn't enough. Cross-validation is only a noisy estimate of your prediction error, and it highly depends on the number of samples that you have. If you only have 100 samples, which often is the case, we don't have that many data, especially in science. That means our confidence interval is 18%. So really 9% on each side of our cross-validation score could still be a valid score. So if we get a 90%, it might be somewhere between 81 and 99% of accuracy in this case. And even if we have 10,000 samples, which already goes to the limit of a lot of the more simple methods, we still have almost 2% error on our estimate of our loss in the cross-validation. So despite doing cross-validation, especially when we think about Kaggle, where a lot of times you are winning by 0.001%. So it's really just getting another sample right. And this is not a case where cross-validation is getting you anywhere. This is just sheer luck. You absolutely have to ignore model simplicity. This is an example where they used a deep neural network to predict earthquake aftershocks. And I love this paper. It was a collaboration between Harvard and Google. It got published in Nature. The problem is another earthquake scientist, a seismologist, has basically gotten the same result with a single neuron, with logistic regression. So really always look for an analysis if a simpler model can do. And that means having a dummy classifier. I mentioned I love scikit-learn, right? They have this dummy classifier, which is essentially a coin flip, but a smart coin flip with as many sides as you need and class imbalance in there. Fit a linear model and usually fit a random forest because they are really good. Having those models on the back burner to back up your more complex models is usually a very important step. To crash and burn, you always want to trust counterintuitive results. Carl Sagan said it really good. Extraordinary results require extraordinary evidence, and even more so, in my opinion, on machine learning tasks. Now, let's get into it because there's a lot of questionable applications now, like predicting your face from voice. where they're like, yeah, but we only want the general phase, which is problematic. Or this startup that is making hiring decisions based on video. And like even the Washington Post is writing, outside experts call it profoundly disturbing. And I agree with them, because over the years, again and again and again, all these systems that do facial recognition have shown bias against especially gender minorities, so often women, and racial minorities. So people of color have often been disadvantaged in here, most recently seen in the Zoom feature, and Twitter showing more white people than people of color in the focus selection of images. So not great. And there's a lot of research into this. These videos and the tutorial on fairness by Gebru are really interesting. So if you do research on that affects humans, you probably want to have a look into bias in machine learning. So really have a look at these. A lot of decisions have unfortunately reinforced a lot of bias that we have in society. And I don't think that's necessary. We can really work together to have a more equitable future. And talking about these experts, we also have experts in physics. So a lot of times data scientists come up with these wonderful models, but they have non-physical results. So explaining that is quite easy to a physicist. I don't know if I can do it as well on a layman's group, but essentially the idea is that if you have observations, then these observations can oftentimes be explained by multiple different explanations, by multiple processes that would generate this data. In machine learning, this is just as true. So your machine learning is just a big, big gradient descent, and it's a non-convex gradient descent. So, well, at least for neural networks. And that means it might, there are different minima where your machine learning model might end up. And that means your machine learning model might find one of the many explanations for your data. Explainability shows how a machine learning model thinks. Explainability is really important in my opinion, but it can lead you down the wrong path. So having a look at the confidence of neural networks can be really funny, because on the top left, the neural network is 99% confident that that is a sea lion. And on the bottom right, that is clearly not a jigsaw puzzle. The problem with explainability right there is that explainability will explain to you why the neural network thinks it comes to this conclusion. So first of all, getting from these 99% neural networks, a lot of really good machine learning models are quite confident in their prediction. So what we want to do is use calibration to actually get them to a number that reflects reality a little bit more. So ideally, we want linear calibration on our models. And I love scikit-learn. Did I mention that? They have a cross-validation method for calibrated classifiers, which can calibrate your random forest, can calibrate your SVM, and those models, while being really powerful, you cannot use their predicted probabilities as a confidence value, just like you can't do it really on these neural networks. Now, SHAP, for example, is a library for explainability. It's an amazing library. I really love it. It's been published as a Nature paper. And the idea is that you have your black box model, and SHAP can then calculate the impact of each variable to your output. And while that's great, the methods used in that will explain to you why it came to the decision, even if the decision is wrong. So it doesn't really tell you causal information, but rather correlational information, why it came to this conclusion. That's kind of the divide between explainability and interpretability. So explainability with SHAP, partial dependence plots, LIME, feature importance, really great methods, but they are post hoc methods. So after you've done your training, after you've done your model fit, you can then have a look at how this model explains its decision. But that doesn't mean that this model has any idea of causality. For that, we have to go to interpretability, which are often Bayesian methods, linear models, and things like explainable forest, causal trees as well, and rule fit. To make your model crash and burn, you have to assume your machine learning model can outperform your assumptions and baseline data. This may be a little bit abstract, but let me try to explain it in a way with reinforcement learning. Reinforcement learning often uses environments to find something, to learn something, to teach a robot. Now, the environment, the robots can only get as good as the environment. So there's, for example, a Tetris reinforcement experiment where at some point the agent, the robot, figured out that if the robot pauses the game right before it would lose, it never loses. So it can only get as good as the game environment is. And this is also true for a lot of other machine learning models. So one application that I was working on can extract data with a base model that uses correlation. So you correlate two time series to each other and look at the shifts, and those shifts are sometimes what you want. But those are 1D correlations, and my data is actually in 3D. So when I use these 1D predictions in a neural network, which can predict in 3D, I still have this bias or this information baked in as the assumption in my neural network that this 1D information, this 1D extraction process gives me. So really, when you do this kind of work, especially in a scientific application, you have to be absolutely careful how you generate your data and what sort of modeling assumptions you put into your data. Now for the speed round. When your machine learning model isn't scoring perfectly, you can still spice up the results. Cherry picking. Cherry picking is really common in natural language processing, where you just generate a bunch of sentences, and for your paper, you pick the ones that look best. On images, you pick the ones that are most interesting, so it gets published. It is quite common to overfit your method on the benchmark so that your method looks more important. There's a really interesting paper linked, which basically has a look at if ImageNet classifiers actually generalized to ImageNet, and they found that a lot of cases it is not the case. The inverse crime is something from math and physics, which essentially states that you cannot use the method to invert your data. The same thing to find the underlying information that generated the data. So if we know the generation process of some data source, you cannot use that same process to get back to your causal information. That is the inverse crime, because you already know this is working backwards and forwards. One of my favorite ones, measuring what is easy instead of what's meaningful. And step counters are one of those things. Step counters have more of a weak correlation to actual fitness, whereas like heart rate variability has a really good correlation, but heart rate variability is much harder to collect. Also quite common in machine learning, where some classes are just really easy to label, Whereas the harder classes, the really interesting classes as well, are often, well, a little bit neglected. To absolutely make sure your model is guaranteed to fail on contact with the real world. Use nothing else but accuracy. Under no circumstances shall you spend time on validation. Like, your model is gonna be fine. Blindly trust counterintuitive results. Counterintuitive results are amazing. Immediately go to the press that you found the newest, best AI in the world. And explainability is overrated. If you use it, it perfectly explains everything. It's kind of a Schrödinger's explainability. And of course, take all the points that are made here as gospel. So thank you for listening. I hope you found this insightful. I had a lot of fun, and I'll see you in the Q&A.